I'm ready.
And let's start.
Right, yeah.
So good afternoon, everyone. Good afternoon, Dr. Jino George. Today we are into the sixth session of National Level Student Enrichment Program for Strengthening Chemistry Fundamentals, funded by PBT Star College Scheme, Government of India. The program is scheduled in such a way as to cover the fundamentals of 9 topics in 9 weeks. So we started this program in September 21st, and we had seen a very great response from the students from various parts of India. We have already completed 5 sessions. First one was on thermodynamics by Professor Arnab Mukherjee from IISER, Pune. Second one was on chemical kinetics by Dr. Jagdish Kumar from IISER, Tirupati. Third was on electrochemistry by Professor Mustafa from IISER, Pune. And fourth one was on oxidation reduction in organic chemistry by Professor A.T. Biju from IISER. And the fifth one was on uh, aromaticity and pericyclic reactions, MO approach to organic chemistry, again by Professor Biju from Indian Institute of Science, Bangalore. And today we are sixth session, and today's topic is spectroscopy, and we have got an excellent teacher from IISER Mohali, Dr. Jino George. On behalf of St. Joseph College, Devagiri, all the students, all the participants of this program, I extend a warm welcome to Dr. Jino George to this program. Now I welcome our HOD, Dr. Tanya Francis, PPG Star Coordinator, Dr. Manoj Matthews, all other faculty members from our college and other colleges, all the dear students in this program. Now let me introduce Dr. Jino George. Personally, I have very close association with Dr. Jino for the last 15 years. Dr. Jino is basically from Kerala, did BSc and MSc from the University of Kerala, and did completed PhD from National Institute for Interdisciplinary Science and Technology, Trivandrum, in 2012. And then he moved to University of Strasbourg, France for postdoctoral research, staying after 5 years there, joined at IISER Mohali as an assistant professor. He has more than 30 high-quality peer-reviewed international journals, and has many projects are handling from various funding agencies like CERF, DSG, and all. And he's a very excellent researcher as well, and his research area is light matter strong coupling and the formation of hybrid light matter states. So I think we have got the most appropriate speaker today. He was one who is actually working on light matter interactions. But I think your research area is something which is not very familiar to us, which is strong coupling and all. Maybe at the end you can just introduce what is that thing, what is the strong coupling, and how does that particular state is getting formed if you get time. But this is again basically spectroscopy, it's light matter interaction, and we have got the most appropriate resource person. So welcome Dr. Jino to this program, and we can start the class. Out to you.
Thank you, Dr. Jamal. It's nice words of introduction. Thank you so much. And also, I'm very happy to be back to Calicut University. So I studied, maybe I missed some of the initial parts. So I studied in St. Mary's College. 2014, I was my batch was 2002, 2004, I'm sorry, not 14, 2004. And I happened to be one of the first batches in the semester system in Calicut University is introduced, okay, that time. So I don't know whether Joman also overlapped the same, right? I hope.
Yes.
So I have a lot of good memories. I remember some of the examiners also from Devagiri College. So it's a great pleasure for me to be here on this platform and talking to many of you. Thank you, the head of the department, Dr. Tanya, as well as others colleagues in the department. I don't know many of you, but yeah, anyway, we'll keep in touch, and then the progress we'll see. All right, so I John, can you also update me, like, like most of them are students, right? Like that we have been interacting with them.
Yes, yes.
So
Mainly
they
BSc
have
students,
BSc and MSc background.
PSC background, majority.
Chemistry.
Chemistry, physics, and we suppose some biology students as well,
All right.
but mainly from chemistry.
Okay, great. Okay. So on the onset, I just want to say, like, spectroscopy is a very wide subject that you will see that I enjoy doing that subject because it has a lot of opening and it has a lot of applications in the scenario of interdisciplinary research. I myself working on an interdisciplinary area. My idea is to give an interactive session, so more than giving a lecture, that may make more comfortable for me as well. But I have only problem that I have only one screen that I am presenting, so you have to stop me if I do stuck or maybe things were not clear to you. You please stop me in between. No, don't hesitate to stop me. Even if anybody, students, have a question or something like which come logically, or you can spontaneously stop me, and then we can discuss, and this interaction should go on like that. I feel comfortable that way. Great. So, as Jomo explained, I am coming from maybe the other part of India, so a bit far, around 2,000 kilometers far from Kerala. Currently, our institute is IISER Mohali. See if I can use the pointer in the beginning. Am I audible, right? I'm audible, clear to you?
Yes, yes, you are audible.
Okay,
Clear.
great. So I'm from IISER Mohali. So IISER Mohali is actually in Punjab state, but you can see that it's a tri-city, we call it tri-city. You see that Mohali is here, Chandigarh is here, another city is nearby called Panchkula that shares Haryana. And Haryana and Punjab have the same capital, Chandigarh, and we are actually in this tri-city, and IISER Mohali is somewhere here. So you can see her in the corner, and we have an airport nearby here. This is a common airport shared for the three cities. I don't know how many of you have visited Chandigarh. You are most welcome to visit us. It's one of the greenish place and one of the well-designed city in India. And well, I mean, it's a good place. I really. I'd be happy that if any of you are interested to visit Chandigarh in the coming time. So you will definitely enjoy here. Great. So IISER Mohali established in 2008, immediately after 2007 and end of 2007, and our campus has been built in 2011 in the new campus. And this is actually the academic building. I am sitting somewhere here. Actually, this is our offices here. And you see that, here the constructions of buildings are completely different style. That's particularly following Kanpur. The founding director was Professor Satyamurthy. So currently we have mainly six total department running in the institute. Four on the main subjects like chemistry, physics, biology, and mathematics, and we have also energy and environmental science, earth and environmental sciences, and also humanities sciences. These are the two small departments other than the conventional departments. And you see that many of the departments, we don't have individual buildings like that. And instead, we have a scattered assembly of groups, labs working. Most of them are working on interdisciplinary area. For example, I am working in the interface of chemistry and physics. So it's like there will be plenty of groups here. So many of them are young people, having a group dynamic young colleagues. So this is about IISER Mohali. This is my group. We are currently our group is roughly around 4 years old group here. In 2017, we started this group, molecular strong coupling group. Here we work on strong interaction of light with matter. Especially we confined light to any particular geometry, and then study its effect. Basically, it undergoes interaction with the molecular states, and then it's basically change the molecular property. The formation of new states occurs, something called polaritonic states. They will be half molecule, half matter states, and so forth. You'll be able to see more information if you visit our website. regarding this, and we are currently working on, part of my students are working on a chemistry problem, some others are working on, this is called polaritone chemistry, other group is working on a problem called polaritronics, in which we try to modify electrical and charge transport behavior of materials, and another group is, we have three parts, another group is working on spectroscopy, pure spectroscopy of these newly formed hybrid light matter states. This is all about my group. I hope at some point of time some of you are interested, please contact me. If you're traveling to Chandigarh also, if you're traveling nearby places, please contact me. You can of course visit us, and we can have interaction regarding research and other aspects. Great. So, okay, this is our apparently a new lab which has been started 2 years back. Actually, these labs are been transferred to us 2 years back. Now, I mean, we are enjoying the new opportunity given to us, actually. Great, so I will anyway ask Jomo and explain maybe if I get some time, because it's actually given with three lectures, 1.5 hours altogether, to explain spectroscopy to you. This is a very difficult task. I don't know how much I can able to transfer. I mean, maybe that's why I felt that it's a kind of an interaction. So if I can able to wind up in a peaceful way, that in the end we are able to discuss some aspect of things that we are doing in the lab. Okay, but maybe we'll see how time progress. Great. So set to go. So it's already 45, so I think we can start. So my idea is to give you, maybe I thought it'd be more interactive that way, that to write something and then invite your attention. So I will be following the book of Banwell and some other books. Banwell is the major core of the talk, especially today. And my plan is, again, today I will introduce the basics of spectroscopy. Tomorrow I will start to discuss about rotational vibrational spectroscopy in detail. And the third day I will cover about electronic spectroscopy. I think that's maybe the best I can do, so that I can at least transfer some of the things, or at least share with you some of the things that we discussed. Another aspect is that maybe I will also tell you, like when we do interviews and other things in our institute, we used to ask students like questions which comes coming out of the box, like, not what you've learned in the course, or maybe more on a fundamental aspect, or maybe on the side in which some history of the science has been originated and so forth. That may trigger you a little bit, so that it will slowly drag into the basics of the science, basics of the spectroscopy. So that's what I will try to do. Let's see how it progresses. We can, of course, if it is, I definitely would like to get your feedback if possible. Great. So, what is spectroscopy? The first way that comes to mind, that the experiment done by Max Planck long back in 90s, in the beginning of 20th century. So Max Planck introduced the term photon, you know that, right? So I am writing Max Planck here. Let me take the pen. Okay. So if I talk about Max Planck, there are plenty of things. Actually, the first definition of spectroscopy is also given by Max Planck. According to him, or say a spectroscope, what he does, he tried to probe a process or event which happened between two states. This is as simple as it is. So I will define spectroscopy. I'm defining this as E0 and this is E1. Okay. So I have an event which is happening from here all the way going here. So I can call in many ways, like you start rotational, vibrational, electronic, any other process, you will have these two states available to you, right? Without having this two-level system, you will not be able to do spectroscopy. Okay, so I will give you more hint. Okay, a method of analysis based on interaction of absorption or protection of light by matter. That's the meaning of spectroscopy. It can include electrons, it can include ions, acoustics, it can be light matter interaction at the end. Right? So what it basically do is to measure this difference, delta E. Okay? this difference delta E. So delta E is actually difference in energy between the two levels, right? So what are the main components? Light. First one is light. Second one is matter. I call matter can be molecule, it can be electrons, it can be ions, it can be acoustics, and so forth. You know, when you read about solid state and so forth, it comes acoustics come to play. Sometimes ions comes into play. Sometimes phonons comes into play, and so forth. I am not able to. I mean, those things cannot be covered, right? Any process like absorption, emission, lasing, stimulated emission, and so forth. Any of these processes which is happening between these two states. So these actually not so familiar to people before Max Planck introducing the term H. So I say Max Planck introduced the term H, which is called Planck Constant, right? Called Planck Constant. I don't know you are familiar with this term, right? So Planck Constant. Yeah, so I think there is C missing. Okay, there is no C here. Okay, just correct me if I'm wrong. Or there is a C. I don't know. Please check it. Okay. So yeah, it's here also. Planck constant, which is H. When it happens is that when he was looking into radiative emissions, or what you call the black body, which is emitting. He wanted to find out what will happen to a black body if it try to emit with respect to temperature. So he looked into the distribution. So you remember, maybe you have studied this called the population density term, which goes as 8 pi h v cube divided by c cube into e power minus kVt divided by, h nu divided by kVt. So, this particular expression, Max Planck introduced, he basically correlated the temperature and the frequency and the population density term. I'm not going to discuss this, but what I am showing you here, this particular constant he has added. Okay, this happened in the beginning of the 20th century, okay, or something around 1909 or 1910. Okay, so this H has a lot of meaning because when he did experiment, when he was plotting temperature versus population density, he got this as a constant. Now you know H is equal to 6.626 into 10 power minus 34, right? This value you know, right? So this value has a meaning. It is okay. This is kilogram/meters per second. This value you know, and this constant. Even I was reading the history about it, how hard to find. I mean, it's long back. When the origin of spectroscopy, people were trying to calculate. There was actually around 10 years of time, people were just trying to calculate this H. Okay, some people got 6 points. I'm saying this is 3 digit, right? Up to 0, 6.626. It can be 6.2. Some factors. Eventually, finally there is a standard value that came to you, that is 6.626. So after this 3 digit, there is numbers, but we normally skip it. Okay, that's so important. So Einstein, basically, he took this relation. And he took finally this as this excitation event, delta A, which is equivalent to H into nu. Okay, so this delta E is connected as H into nu, which is H is a Planck constant, and this is the first time Einstein used it. So he appreciated what Max Planck did. Okay, a couple of years before. That basically helped him. So now these energies defect. You know that H nu, right? Right? H nu is called the energy of a photon. And what is photon? Photon is a quantum of energy of light, which is traveling as a wave packet or as a packet, right? So Einstein now defined it as H nu that has a given energy, it is quantized. So it is something fun, like then Einstein used the Maxwell expression and explained it. I hope that you have seen that how the whole concept has been merged and slowly put up, how this came up. Then there is another factor about, I said that when you deal with spectroscopy, you deal with light, I said, right? So these are the questions we normally ask the student, what is a light? So automatically students say that it's the electromagnetic fields are. So it's electromagnetic field, right? Electromagnetic field. So what do you mean by electromagnetic field? So light has a peculiar property, okay? Light is something sometimes called as transverse wave, right? Light has a peculiarity, it is called as transverse wave. Why? Always you have electric field which is perpendicular to the magnetic field all the time. There are other cases, okay? That's why when you see, I'm talking about electromagnetic field, we said photon, it is a quantized form of energy of an electromagnetic field, and electromagnetic field is always look like transverse wave. So that's fun, right? This is how the nature of light comes in. So when you define it, so it is something very interesting. So you start from, I can just define light like wave function, or in any waveform, for example, I take it in a waveform. I have, for example, this case, I take maybe a function which goes as y is equal to a into sine theta. Okay, this is, you can call as a sinusoidal function. It's a simple harmonic wave or sine wave function, right? So here I am seeing that when light falls, so maybe that's theta is equal to 0, it goes like this, then it comes and then, you get a minimum here, you get a minimum here when theta is equal to 0. This will be your pi, and this will be your pi by 2, right? This is the amplitude you call, right? You call this is your amplitude. And this is your antinode, and this is your node. It goes on like that, right? So this is in terms of 2 pi radii, right? So now what I did, now I think I can see when you see the book of Barnwell, it is very beautifully written. I encourage you to read it. I think, especially even if you have done master degree, or maybe the Barnwell book is actually a benchmark that we normally follow to explain this very clearly. I mean, this part is very well written there. So I can represent thinking about a dipole which is changing. This is another way of representing. I'm thinking of a dipole, so I have a point here. Then I'm placing a point here like this. So now this is your point P in which a particular dipole is rotating, right? I think you are familiar with this concept that I'll bring the idea of frequency into. Okay, this is circle, okay? This is circle, and I'm making an angle theta here, so it can move, okay? The point between O and P, it is moved, for example. This is O, for example. From here to here, it is moved. Okay, so this is how it goes, and then you know that it particularly make a cycle here. So when I start with the same wave function, I have pi by omega, and it goes as 2 pi by omega, etc. Right? So you have same here, your W will be in the y-axis. This is the y, and this is that give you the amplitude straight away. So I mean, there are many ways of representing. The maximum will be here, and this is actually taking one. So it starts from 0 degree to 360 degree. That is 2 pi accumulation. So you can denote theta as omega t, and omega as for taking one frequency, you will say one frequency, 1 hertz is nothing other than omega by 2 pi. Then you get your y will be defined as a sine theta will be equivalent to a sine omega t, which now I connect to frequency v, which will be equivalent to a sine 2 pi dt and so forth. Okay, so this is how it comes out, And now you will end up in again another term. So this is okay. I'm sorry. I have shown you this magnetic field versus electric field distribution. One in XY direction, one in XZ direction magnetic field. They always propagate, orthogonal, or say that that's why it's called as transfer. So you keep in mind that the transfer behavior make you a lot of things here comes out in which you have a phase. Which is coming into. That's how people make chiral or say when you create out of phase and in phase, you can make very complicated polarized light states, right? So that's again another fun. I can also convert this into position coordinate and so forth. When it get converted into position coordinate, you will get something like wavelength coming into play. Right, I remember this also we have appreciated where we can. So I don't have much time. I am just quickly going through y is equal to, you will end up in a sine 2 pi x by lambda, where you call x is equal to c into tau, where c is the speed of light, tau is the lifetime, and so forth. So this is another way of representing the nature of light. So I think this part you have studied. So it's very clear that light has a complicated behavior. So when light interacts with matter, we always consider this effect. Now I will straight away get into the electromagnetic spectrum. Electromagnetic spectrum. This I took it directly from manual. Okay. So you will start from NMR, IISER, microwave, infrared, visible or X-rays or gamma rays and so forth. Most of the time we deal with, NMR you study very well, and IISER partially I can say, okay, so of course it's one of the thing that you used in using your characterization tool. So NMR comes in radio frequency. So you are very familiar, I think some of you may be doing it. The energy associated with the change in just a nuclear spin is something around 10 joule per mole here. So that is why this energy roughly comes around. You can see here, they are all given here, energies is given here, roughly around 10 maximum, we say 1 to 0, when you can see up to here, 10 minus 1 is shown here. 0.01 or 0.001 to 0.1 in joule and joule per mole. Okay, that goes on. IISER is slightly up. So then microwave, electron spin. Okay, this is electron spin resonance. And microwave comes around in the range of roughly hundreds of joules. Okay, this is how rotation around a bond with respect to principal axis. So we consider moment of inertia and so forth. I think you have also studied different kinds of molecules, how rotation happens that create a dipole change in the system. That I will see, or we will see next class very quickly. Then infrared is familiar to you, that happen to vibration, like due to an harmonicity of a bond. Then end up in UV visible absorption spectrum, and then X-ray and gamma rays associated nuclear change, nuclear configuration change, right? And there are one example is this what you call there are spectroscopy associated with that to calculate it. I'm not going into those details anyway. So X-ray also you very well know this. Okay, so simple for rotation. I mean, there is one thing that happens. I remember I was just showing you. You remember I was just showing you this, right? So we have something other than dipole. So now I have a rotational dipole. Think about I have a rotational dipole. So if I write the vertical component of a rotating dipole here on this axis, and it basically moves here. This is how it looks like. So you will see actually a difference here with respect to the rotation axis. So you just start from maybe something like this is the molecule, and it goes this way and then go opposite and so forth. So that gives actually some difference in dipole that create an energy for the system, or it take energy from outside to do this. So that create, an absorption or an emission event. So rotation, of course, it has associated energy that comes in the side already very low energy. So this is how it is. So then we go down like this, and even, I don't know whether you are, being a student, I have never actually measured a spectra in the lab. Okay, like in my BSc, I never. See, we have actually some spectrometer at the time, which was like when it was a colorimetry experiment. But in modern labs, I think maybe Devagiri has one. So you have normal spectrometers which can measure wavelength versus absorption or some function. That's how one simple way of representing, because when we represent any spectra, it has associated x and y axis, right? It has associated x and y axis. So here it is a I can think about transmission. Okay, transmission, which we can measure with the UV, for example, UV visible spectrometer. Here I will write wavelength, right? Wavelength. Okay, or it can be frequency, it can be lambda, mu, whatever it is. Okay, it can comes like this, and what happens is you end up in having a beautiful spectrum, right? So this will be either a Lorentzian shape or a Gaussian shape, depending upon the system. So I am not worried about that. In reality, when you do a calculation, you get, instead of that will be a line. We assume that it's a very sharp line, but instead of a line, we are getting a broad, or maybe sometimes very sharp, or maybe an intermediate Lorentzian envelope, depending upon the molecule of your interest. This is due to many other effects like natural line width, what you call natural line, homogeneous and inhomogeneous broadening in a spectral measurement. Right, so we can literally measure T versus lambda, many options, right? I was just in T versus omega, V bar, which is in low numbers, and then you can have R, then you have I, you can have absorption. So many options available for you to measure something, right? So again, Jomon, am I audible once again? I'm not getting any feedback. So is that okay? I can ask you once again this, am I going in the right page?
Yes, no problem.
Okay. Okay, is that fine?
Yeah, fine.
Am I clear?
Yes.
My screen is also visible, right?
Yes, no problem.
Thank you. Great. So what is very important is that you have to use, whenever you use this technique, suppose here I measure something. You can see here, I don't know, maybe you being students, you might have already measured some absorption spectrum of a molecule, potassium permanganate. Okay, potassium permanganate is a molecule that we used to give students here in IISER in their second year or first year to measure the absorption of its what you call metal to ligand or metal to ligand charge transfer band, right? This MLCT band. So they comes around 540. Get an envelope which is vibronically coupled to electronic states. You get an envelope, beautiful envelope, you remember. I don't know whether you've measured this. This is the one we normally use to quantify the amount of potassium permanganate, something like this, some spectral envelope, right? To think about this. So what instrument does, it try to measure from all these points. Start from maybe 700, for example, this is 700 and this is 400 nanometer. It tries to measure this point, goes up, and then there is a difference, then you measure and give you, right? So there is a corresponding instrumentation behind this particular measurement, and basically measure with a given time. This is static spectra I'm talking about, and to build your entire spectrum, right? You can do this for vibration, you can do this for rotation, you can do this for any other measurements like electronic or whatever. So it's involved measuring individual wavelength, right? So there will be corresponding instrumentation associated with this, right? So let me check. Yeah, so I have finished maybe 20 minutes for the basic introduction. So now what is instrumentation part? Here, if I want to measure 700, how it go from 700 to 699 and 698? That you tell the instrument to move very precisely in wavelength or wave number, right? And that's how it measure it in a static measurement. We will see time domain later, but now in static. So there will be a particular process which is happening that include many components, like you should have a source, you should have a detector, you should have something to separate the light which is continuum coming from the source to the detector. We call wavelength selector. So the wavelength selector pick a wavelength and then goes on like then you get actually, and then here transmittance is directly recorded with respect to some blank. Okay, this let us skip. I mean, how you measure and so forth, we will skip. Now, why absorption and emission happens very quickly? Because instrumentation I will not go into detail because that is again another difficulty of being discussing in a very short time. So anyway, but in the later part of this talk, I will quickly show you what are the components of a spectrometer. So why absorption? So this you already know. I mean, I can write a very simple way of this is to show you why absorption. Easy way is to see what you are naturally seeing, some colors, like you take some molecule, like potassium permanganate, you put it into water, it gives you some color, right? Some color, and that color is due to what process? It's a process called absorption. So you have a ground state. I am representing, okay, this is my energy. This is internuclear distance. Okay, this is internuclear distance. So I have a common ground state, I call ground state, and I have an excited state. Okay, so an event happens, so I have a ground state which has a V0 level, right? I will come that tomorrow. What is V0? Which is a 0 point energy. So you have an excitation which happened from here all the way up to the next level. Okay, somewhere here, it goes somewhere here. Then the system will have many vibration level, like here also, many vibration level, and then it relaxed, come here, and then fall. It comes to some of these levels. Okay, and also it can dissipate to the medium, like for solvent or so. This is absorption, right? This is absorption, and this you call emission. Emission has many names: fluorescence, spontaneous emission. Some people don't believe actually what exactly means by spontaneous emission, and so forth. But you know, when I was asking, this absorption event happened very fast. Okay, this is we say talk in terms of dynamic. This happened in 10 attosecond, very slow. 1 attosecond is 10 power minus 18 second. Okay, this has happened much faster than a femtosecond laser work, so you're not able to really record it like its dynamics. How all of a sudden light get excited. So I was thinking, suppose this is a dynamic process. You see that an event happening from here. This is a wave packet. So you can also, of course, write how the wave function look like, right? I think some of you are familiar with this. This an electron density boom goes up here. It comes here, then this process repeat, right? It goes up, comes down, goes up, comes down. So always what happened, even according to the definition, even at absolute zero, you will have some event. This is 0 point energy, right? You have some event which is happening in the ground state. There is an excitation here, but electronic state, you can see still excitation, which goes like an electron density goes from ground to excited state, come back, goes up, comes back. It's an oscillation. All right, this oscillation will create something called transition dipole moment, right? This transition dipole moment will depend upon, okay, your ground state function into energy into R into your excited state function. Okay, goes like that. So, so if I consider ground state, this is actually the entire wave function of the ground state. This is my excited state and so forth. This is how you define it. Right, so I will also not go into these details, but what I will try is that something we missed actually when we try to learn this. The important thing is that long back when Einstein introduced delta E is equal to h nu, okay, he basically also proposed that now let's look emission. I say emission I am seeing happening from the lowest energy level. right? Lowest energy level, this is V dash is equal to 0, which is, okay, this is the excited state, right? From here it is falling to the ground state. So when a molecule is emitting from here to here and a molecule is absorbing from here to here, that can be connected to one equation. So that's why he took these probabilities of different transition and put it together in one frame. This is called Einstein Coefficient. I don't know, you familiar with this? Coefficient. Okay, so Einstein Coefficient is you have a particular event. I take this transition, which is you call it as absorption. See, any of these cases, when I will normally write, if I now I know that this is actually going up and coming down, so I will put double-headed arrow. I have a reason to say this. It still conserves the energy, okay, and I will have the oscillation going up and down. So maybe we will skip that argument, but this is maybe in the modern textbook you'll see that. How does it been explained? That means a benzene molecule, if absorbed, it's always oscillating electron cloud up and down. That's it, the point. So let us skip this, because if you see that you will also get confused. So Einstein was just putting the arrow up and then saying that this is rho of V of B12 and other one is of V of B21, and there is another process which is called rho of it doesn't have, it is instantaneous, so it is A21. Okay, so these are the three terms, B12 for absorption, B12 for absorption, okay, and absorption, B21. Did I make something wrong? No. This is stimulated emission. Okay, so A21, it is called your spontaneous emission. Actually, Einstein started calling it as spontaneous emission, There are a lot of other controversies regarding spontaneous emission, whether it can be called as a spontaneous process. That I am leaving you. You can read it. There are some arguments which support it. There are some arguments which doesn't support it. Okay, that's none of our business to discuss this now. Anyway, so B12 is the Einstein absorption constant, and B21 is a stimulated emission. So what Einstein did, he took this B12 rho of V plus rho of V of B21 plus A21 equal to 1. That means your maximum probability is 1. He said that I have all the possibilities. One is absorption, one is emission, stimulated, other one is spontaneous. So now I put up all of them together, I have to get 1. So he basically brought all of them together. So actually you see that this one is just opposite of absorption, right? Stimulated emission. There is nothing other than, you see, best example is lasing, light amplification by simulated emission of radiation. So this is actually nothing. So opposite of absorption, you get actually a population inversion in the excited state. Okay, I forget also to mention this is 1, this is 2. Right? So then I jump from, I fall from the higher state to the ground state. Just you think about just inverting your absorption state. Right? Whereas A21, it is following some dispersion or dissipation in the energy, like to other degrees of freedom and so forth. Then fall into the lower state here, V0. And then from V0, it falls as a normal spontaneous emission. Right? And this has been proposed, I mean, say, Michael Kasha, a famous scientist, photochemist, he suggested that you can have, this is called Kasha rule, that you would always fall from V dash is equal to 0 of the excited state to the ground state. There are cases which don't follow this also. Okay, so that is how it looked like. So I have to now represent the distribution. So this is condensed form of that equation. I am not going. This has been taken again from the Max Planck equation. So I was showing you before. You can even, when you look into the distribution laws, you will get those details very well. Okay, so let me go another concept. I mean, let me take you to another concept. Being a chemist, that I was always enjoying, that when I connect absorption to number of molecules present in a system, right? We always write an expression. A is equal to epsilon C, right? A is equal to epsilon into C into L. This expression is much familiar to you, right? So I have absorbance. This is absorbance or absorption. Absorbance. This is molar extinction coefficient, right? So this is concentration, this is length, right? So you have there are 4 terms. This epsilon, which is called molar absorptivity, molar absorption coefficient, absorption cross section, and so forth. There are many names to it. Okay, so it is simple that if you take a block of absorbing material, you measure how much light is passing through, transversing through, and you get a particular term, right? So this has been very well known. Why chemists used it? Chemists used it to quantify the number of molecule absorbing. That means extinction coefficient, which will be represented in centimeter inverse, mole inverse. Okay. There are some very good books that discuss how this is being derived very well, very clearly in an absorbing medium. Okay, with you know, you have a block which is absorbing. You define its area, and then you take area cross section, and from there you calculate how many atoms or how many molecules present in that area cross section, and so forth. Then you convert this into number of molecules present and then concentration. You get a constant into something called absorption constant into B into C, or into C into L, sorry, the concentration into length. So this epsilon is intrinsic to material. Okay, some material has very high epsilon. I know some cyanide dyes. Okay, cyanide dye, very strong absorbing dyes. Their ground state, and you remember this graph I was showing. This particular is actually again a schematic. Okay, it's a schematic representation. I have not represented the actual coordinate. It's just a scheme for you to show. So many molecule. This is your R equilibrium, right? With respect to the ground state, the excited state is slightly pushed or moved. Okay, either this side or this side. Depends. Okay, so I can have something like my Planck quantum transitions. I think you are also familiar with this state, which is the transition maximum probability. That also we will see later, if I get time in the last class. So here what I am saying, that cyanide molecule is a molecule in which their ground and the excited state has the same conformation. That means their R equilibrium are the same. So what happened? Then you can have a transition which is vibration independent, and it's called vibrationless transition. In this case, you get very high extinction, roughly 1 into 10 power 6 centimeter inverse, mole inverse, centimeter inverse, mole inverse. Okay, a very high value. But normal molecule, like you think about, maybe some of you are familiar with a normal dye, like a Berlin diamide, or maybe, for example, benzene. Benzene has an absorptivity roughly 20,000 centimeter inverse, mole inverse for the fundamental transition, something around approximately. So you see this is very high. So it purely depends upon the molecular system how this is being explained. Okay, so this value has an importance, that it is the ability of a molecule or a group which can absorb energy. Okay, so that much is important as of now. If you are interested further about this, of course you can read it. It is given in many references. If you can personally write me, I can give you good references to know more about its complication also. Normally in physics, people don't consider Beer's law for calculation because always anything which is associated with the system which has its own scattering. So I will go back to my old story of Einstein Coefficient to correlate to make a very clear understanding than molecule. So here there are so many assumptions Beers did to, this is called Beer's Lambert law in general. You have to get a linear function with respect to concentration. Then only the law works, otherwise it cannot. That's how we do colorimetry. It has its own importance. Okay, great. Do you have any questions until now? Then I can go to the next level, maybe next little bit more about how the light behavior towards molecule and so forth.
Students, you can use, if you have any questions, please unmute yourself and ask the questions. I think Dr. Jino, you can continue because they will put some questions in the chat box, and that's all.
Great, yeah. So I am now switching into something which is properties of light again, because I felt that should be discussed to chemistry curriculum as well very clearly, because this will help the students to understand. I think you have studied some of these very simple aspects in your higher secondary school. Maybe part of your physics, subsidiary courses as well. So when I consider light, we are already thinking, okay, so light is actually, it's a packet of energy which is propagating, right? So it depends upon the medium, the light will have different speed, right? So the first term which comes into my mind is, first one is refractive index. I don't know the students are familiar with this. I think most of you. So I will explain why it is, what it is. It's a quantity which normally connect N is equal to velocity of light in vacuum divided by velocity of light in the medium. Okay, so I can easily define refractive index, in which we use it for many purposes in our lab. Okay, that's why I'm so specifically saying it. So, for example, when I have a molecule, when I have a light which is traveling in air, which has a wavelength of 500 nanometer, the moment, so air refractive index, okay, I can say it the other way, air refractive index, if I take 1.003, actually approximate, it's again approximated because you have to approximate to vacuum, okay, right? So air can still stop light little more than, so some amount. So vacuum has a value which is taken as 1 thrust values, right? So that's called vacuum permittivity. We'll come to vacuum permittivity later. But when it enters into the glass, what happens? Glass will have some 1.5 to roughly around as its index. So what happens is that the corresponding, you remember when we are talking about when light is traveling across, it can have displacement coordinate. Then what happens that your wavelength, which is connected to displacement, short down by some amount here. This case, if you just calculate 500 divided by 330, you get roughly 1.52 or 1.5, okay, approximately. So that much is the difference comes. So we see that my wavelength changes. What is the effect? My wavelength change. That means in a medium, when I enter, light enter, it changes its properties. So this is something fundamental. I mean, very interesting as well, right? Then it comes out. I will show you a problem very soon. You will see, you'll appreciate that. So I am skipping the other aspect of what you call, what is vacuum permittivity, how vacuum is being defined, what is epsilon zero, what is its correlation with mu, and so forth, permittivity of free space and so forth. So that you can check. I think it is beyond even the scope for the class. So you slowly check about it. So, but I cannot avoid mainly three things. I cannot avoid these things. First one is refraction. Second thing is reflection. Third thing is diffraction. Right? These three things are very important. I think you've been in chemistry courses, I don't know, maybe in BSc level, it has been not taught much, but maybe your subsidiary physics, there are also some physics students, they might have studied this very well. I'm talking about the basics of it, but that will help a lot actually. So what is refraction? Change in the direction of the light when it come across a boundary or an interface, right? So there are plenty of examples. Right, this particular case, when I am entering here, my index of the medium was 1.0. It entered into water. Here, this is static water. It has an index of 1.33. Then it basically, so you can see here also, this is the bending of a pencil in a water. So what happened? That when your eyesight, you see that the light is traveling with different speed in air and in water. So this will be having 1.0, this will having 1.33. So that make the stuff bend. Actually, your eye will feel it that is bent. So what happened? It's a basic concept of n is equal to C0 by C. So this expression is valid here, and many cases I was just mentioning air. I'm not going into even draw how does it look like and so forth, but you can appreciate it when you read about it. So I think I encourage you to read about it. So air has 1.00, yeah, 30 and 3. So this is where, this is again approximated, okay. This is the index has been defined. Water has, so these are the main things that we normally use when you even measure spectra. You will use it. Glycerin, many things has been, I'm just showing a few of them. Glycerin has an index of 1.47. And so on. Glass I already mentioned, right? Let me mention also glass 1.52. So this is the ability of a material to stop this the light, right? So it also very importantly, what happens that it changes. You already know Snell's law, right? Snell's law, you have studied it. So what you call sine theta 1 by sine theta 2 is equal to n2 by n1. This particular law you know, and even here the theta is now depend as a function of, that's most important, to become a function of wavelength. So that's why your refractive index, when you plot any material, you will see Ri will become frequency dependent or wavelength dependent. You will see a normal dispersion, something like this, and all of a sudden you may see some anomalous behavior also. Okay, this is called normal dispersion of, it is wavelength dependent. It's very clear for many material. It may be also flat for some material. Some common good solvent will have the dispersion of refracting index will be normal, but many cases it can be also anomalous. Okay, anomalous dispersion. So you can check these details. There are many websites. One of them is refractiveindex.info. If you see that there are graphs given how the spectra of a compound or a solution or a material or a solid, how does it change with respect to wavelength by applying simple refraction law. Okay, so I think that's enough for understanding what is refraction. So yeah, so this is another one way of, I was saying the use of it is being used in just using a prism. You see you can able to disperse the wavelength of white light, the application of refraction, right? So there are many things similar to that, which is maybe you can read about it and then appreciate it by yourself. Great. Then what is reflection? Reflection happens when along with refraction. So that's actually again a problem of interface. Okay. So most of the time reflection occur along with refractions, and it always happen if the material has a very high difference in index. Okay. If n1 is not equal to n2, you will have this event seriously. And if the n1 and n2 are far apart, then you have a very strong refraction. from the system. And that is connected by the so-called Fresnel law, IR by I0 is equal to N2 minus N1 all square divided by N2 plus N1 all square. And this expression you will be able to calculate the reflection laws in a system. Okay, what I used to give actually students, suppose you are given with a glass tumbler, you are given with a glass tumbler filled with water. These actually have a thickness, right? Yes, some thickness. This is a glass tumbler. Now light is coming. Okay, you have glass index variation, so you have some amount of reflection. Then some amount of light goes in, it passes through, right? Pass through here. Then again you have another window. You lose some amount of light here. Then it again comes out. So finally you get IR, which is, final I comes out of it, will be a collection, or say that I have one interface I have here, second interface here, third interface here, fourth interface here. So I have to each, and so that's a calculate the percentage of loss of intensity due to reflection. So I can if I already give you a refractive index N1 of glass, N1 of air is, so N air is 1.0003, N of glass is already given 1.52, and then other one is also given for water, N of water. Then you have everything to calculate. So you have to calculate for 4 interfaces, and by doing just light when passes through, you are giving I0 here, right? I0 given. IR first, IR1, IR2 will be lost here, IR3 will be lost here, IR4, it goes on, right? So 4 times it happens, and then you can quantify. And I normally ask, I am given water, and this is the corresponding situation. Calculate the intensity loss. Students can able to calculate it. So finally, you will get, I will give you some value. Final transmitted light will be IP by R0, which will be roughly equal to 0.85. Okay, this is a ratio, that means you lose 8.5% up. 0.085 of I0 occurs. That's what it is finally. So I am just saying you can calculate it. Okay, this is roughly some value of roughly 8 to 9% of loss itself will occur if light transverses medium. This is an approximation again. This is to just show you that how reflection can cause an effect. Okay, next one is refraction. Refraction, you are also familiar, I think, with this term. What I see that we already seen. Sorry, I made something wrong. Yeah. Okay, this is not refraction. This is diffraction. Okay, this is, I think I copy pasted and I put it like that. Okay, so this is the famous Young's double slit experiment. I was talking to students about this experiment. This is one of the beautiful experiments which was done long back. So when we do light traveling through, parallel beams passing through, each of this, like you pass through one slit, this become again a point source, and this point source is passing through different slit. They are separated by a distance, and then it falls into a photographic plate, and then you see a pattern which is formed over here, and this pattern will have a definite size that comes from the constructive and destructive interference of light. Right? That's how it comes out, right? So then we have the famous relation, which we will write n lambda is equal to what do you call it? 2d sine theta, or n lambda is equal to 2d sine theta, and based on that is basically been defined. So there are plenty of problems. So I can define this distance. I can define this distance, and then I can play around. So of course I can write in terms of BC and DE also. It will take more time for us to do this part. So I think I will also skip, but you will see some problem that normally comes with this. So why I mentioned this much to you, that my idea is to show you how an instrument will look like eventually. So any instrument or an optical instrument or a spectrometer, if you take, it has mainly 4 components. First one is source, second one is a wavelength selector, third one is sample, fourth one is a detector, and so on. So here you can see here, each of them is associated with any of these optical phenomena we have discussed, right? So when a source emit, it has to deal with its losses. We start from the Max Planck relation all the way up to distribution law. I didn't talk about distribution law, Maxwell distribution law. So anyway, each material has its own properties. Second one is wavelength selector. Very clearly we have seen it, where when we are plotting a spectrum, each of the wavelength is being resolved very, very clearly in a spectrometer. That comes from a prism monochromator or normal monochromator to very complicated grating monochromators. So I cannot able to go in depth of each and everything, but these are very important components. So that when you talk about grating, you will have automatically interference or diffraction coming into play. So the basics of diffraction is applied here as well in grating monochromator. So nowadays most of the modern spectrometer comes with that. Then you have sample compartment. I have a detector. So I will show you this so these are very broad aspects, like maybe that will be very easy for me to explain you source and detector. Then I will come to wavelength selector very quickly. Let me see how much time I have. I have another 10 minutes, and then I will wait for your questions. Okay, I will wind up in 10 minutes. Is that all right? Am I correct with the timing? Hello, can you hear me?
Yes, sir. That's fine. That's fine.
That's fine. Okay, sorry. So I am only seeing the screen. So sorry that if something is wrong or something is not going proper, please stop me. Okay, I'm very happy. Otherwise, it's not like I'm not able to. I'm only seeing my screen now. Anyway.
Sure.
Sure. Thank you. So, so what I am showing here is that, like when you consider any of these cases, like I was just mentioning you source as like depending upon your use. You remember when I was showing in one of the beginning slide how what are the electromagnetic spectrum look like? What are the range in which you start from? This is called vacuum UV. So normally we don't use it much, right? Some people use it. So you can see that energy is roughly between 100 and 200 nanometer, will be close to like 3, 4 or more than that electron volt. This has been used to get very high excited, or maybe some ionic compound like sodium chloride or potassium bromide and so forth. There are electronic transitions that comes around, ionic transitions comes there, or some higher order excited state of a molecule. Okay, otherwise you have UV region, you have visible region, then NIR region and IR region and Fourier. These are the main window that we normally use for molecule characterization, right? For students, this is what you basically study in a course of a spectroscopy. So what are the lamps? Argon lamp. Argon lamp can give very low wavelength, which means very high energy light. Okay, which is not really required in many of the applications. We normally start from here. So we will either have a deuterium lamp or a xenon lamp in your lab or in your laboratory to do an experiment. Deuterium lamp works based on the photo excitation principle and then radiation emission. Xenon lamp is also similar, right? It can give a continuum wavelength. Continuum, basically it gives a continuum wavelength. There is a distribution. right? It basically gives you distribution of energy. For H2 and D2, I mean, we don't use hydrogen because it's complicated, but normally we will have a deuterium lamp in your lab. Then when you have take a spectrometer or anything, you will have a deuterium lamp, which is again a costly lamp. That you will have a quartz tube filled with deuterium D2, okay, D2, and then you shine light into it, and you give high energy, high electrical energy, then it get electrically get excited, not photo excited, electrically get excited, then they come back to the ground state by emitting. It is coming from atomic absorption of the system, if I'm correct. You can correct me if I'm wrong, okay? So I'm also recollecting my previous understanding. So maybe long back I thought how a D2 lamp works. Xenon lamp, same thing, which also keeps in the range of below 200, but it gives steady current supply, steady wavelength, more or less flat light, so that you can use it actually as a source, okay? And you see LEDs, now you can have LEDs available all the range. Other one is tungsten lamp, which is a widely used one, which basically work on based on the what you call black body emission, right? Black body radiation, based on working principle of black body emission process. So you have a deuterium lamp coupled with a tungsten lamp, which will be used in many of the UV visible spectrophotometers, which cover from 200 nanometer to say 2500 nanometer roughly, or maybe up to 3000 nanometer for your spectral measurements in a UV visible absorption setup. Okay, so we don't normally use Nernst blower. They can give a very lengthy, but they are not so stable nowadays. I don't know, maybe people are using it. It's again expensive. Otherwise, nichrome wires or globar. Silicon carbide is widely used in FTIR or nichrome wires. Now there are alloys, and then you just heat it, they emit a continuum wavelength, a continuum source. It's called continuums. All of them are coming under continuum. That means you get a collection of wavelength emitting with a maximum. That follows, some of them follows, of course, most of them follow Maxwell distribution law, and then you get actually, depending upon the wavelength, they can control the tungsten lamp, which I remember very well. Even Nernst blower also, you can control the wavelength maximum. Okay. Then line sources we use in spectrometer, mainly lasers use actually, otherwise hollow cathode. Hollow cathode is now also not so familiar, like maybe in the beginning where spectrometers was introduced. Correct me if I'm wrong, but otherwise you see lasers. Lasers are a lot now because it's a very good excitation load, because it's a coherent single wavelength monochromatic. You can have a very high energy. It's for special application. And it can also work in time domain because you can make pulse lasers, right? I will come to time domain in few seconds quickly to make you winding up the basic spectroscopic ideas. Then detectors. First one, photographic plate, has been all time people use. I have seen them when long back, J aggregate, one of them, jelly aggregate. These are the first aggregate, people used in export in 1930s. They use a photographic plate to measure the spectrum. At the time, PMT was not available, photomultiplier tubes. Photomultiplier tubes came after. You see, the photomultiplier can work roughly around 150 to say 400, 500, 700 nanometer. It also see 700, roughly more than 700, go 800. So I have PMTs roughly going up to 800 in our lab. Okay, so this is a common used one and have very good sensitivity. It is also very sensitive to light. Okay, so you have many diodes kept at different potential difference, and then you will have a gradation of potential so that it undergo photoelectric effect, and then one photon hit and it eject one electron or two electrons that become amplified double 4, 8, 16, and then multiply. You can have one photon giving roughly around 10 power 6, 1 million photon out of it. So that gives that much sensitivity, and finally we can measure it. right? Another one's a photo tube, photocell, silicon diodes, charge coupled devices, and so forth. So I don't discuss those things. We can have CCD. We have CCD in the lab now, charge coupled device. That's widely used nowadays for both imaging and spectral measurements. Okay, and when you come back to FTIR, okay, which is basically we'll be discussing this in detail tomorrow. We will either deal with the thermocouple, or there are specific detectors, some photo detector, okay, some special deuterated, some particular molecules or materials or complexes they can absorb. It can be made of a semiconductor, it can be made of some, we are using something called deuterated triglyceride, some special compounds that can absorb and then can sense it. Okay, bolometers are used close to micro region, so very far infrared. You see that I can have it. It can go up to here, but actually again costly. So normally it work on resistance. Working principle is calculating the resistance when a photon is falling onto the system. So this is how it looked like, and this is how the distribution, or say that I discussed about source and detector. Okay, here itself actually we can discuss a lot independently, but the last one which left is a wavelength selector. Wavelength selector, I told you just saw previously, I was just mentioning one simple configuration using a prism, right? When you use a prism, when sunlight comes, C.V. Raman used prism coupled devices for making spectra at the time when he discovered Raman effect. By the way, Raman effect is not coming to absorption and emission concept, because Raman is an indirect excitation, or it's coming from a pseudo state. That you may be already studied, but they will come. I don't know whether I will get time to discuss that. Anyway, what is important here, I was talking about a prism. What prism does, it's basically separate wavelength. Now, if you put a slit here, I'll be able to just get the red light out. Same way I can get orange, yellow, which one I want, and then that basically define my wavelength selector, right? So, so I have many ways I can use grating, some corrugated surface. These are another stuff which is now what is widely used in the market and very useful with very high resolution. So same thing, light falls here, you get refraction, okay, then they undergo interference at some point of time. Okay, so you can have interference, they get interfered on another plane, coming AB plane, you get CD plane and so forth, and it goes like in lambda is equal to 2 sine theta kind of an expression. You can, it depends upon the angle of incidence with respect to the normal here. I mean, okay, this is how it looked like with respect to normal of the principal axis. I have to do that, may be easier here. With respect to the principal axis, you plot it theta and r and so forth. So I don't really again discuss this. This is again one of the easiest way nowadays. Gratings are basically corrugated surface, so you basically define the distance between these two groups. This is called d. Once you have d defined value of d, then you will be able to change the wavelength maximum, and depending upon the angle of incidence, we can change. Then you put an exit slit, you collect the wavelength, which is discernible from that particular grating device. Okay, so that's another way of dealing with it. And these are normally, these will be like here, the distance between these 2 points are in nanometers, like 500 to say 1000 nanometer in dimension. That's actually the physical distance between these 2 points. So you can make similar things. In infrared, they goes to be very large. Will be large, we call groups. So group distance, roughly, they can go in micrometers. Okay, so that much I think is enough for the basic understanding of spectral components. So now it comes time domain spectroscopy. So time domain spectroscopy, what we will do, we will convert, a function into as a form. You see here I am plotting PT as a function of time. right? So I need, why it is coming, because so far we were discussing, like when I was explaining you frequency domain. Frequency domain has a limitation. Suppose I want to measure a spectral window, for example, FTIR spectrum, sorry, infrared spectrum. I measure from 7,000 to say 100 centimeter inverse. You see that if I want to just start acquiring the spectrum from 100 centimeter inverse all the way up to 7,000 centimeter inverse, if I take each and every point slowly, 1, 1, 2, 3, 4, like 100, 101, 102, 103, like that, it will take long time for me to acquire the spectrum, first of all. Secondly, I will not able to maybe some particular experiment which are very fast. Okay, that means it's happening so fast. Okay, I will not have a transducer or some detector which cannot able to detect so fast with respect to the change. So then I need alternate ways. So that's why Fourier transform introduced. Fourier transform basically convert what you call time domain into frequency domain. You have a PV versus V comes in. This is the conversion equation. So what is it does actually? That a simple way I can say that to obtain a time domain signal, we can use a method of converting a high frequency signal into a measurable frequency signal. So we will use some retarders, and we use the properties of light, in which light I basically slow down. I will allow the light to pass through some other channel, in which I slow down the time in which this light is traveling. Okay, so light travel with the speed of 3 into 10 power 10 centimeter per second. I know this, so I will put some X delay in it. Okay, this is how all the time domain spectroscopy comes into picture. This is a Michaelson Interferometer here. So you have a fixed mirror here, you have a fixed mirror here, and I have a movable mirror here. And then I will have a common source for both of them. The light will travel over here. Then I will have, okay, this is starting to move from here all the way up to here, and maybe coming back and going here this way. Go to -1 lambda to +1 lambda, and so forth. This is the way that I have a retardation in the light speed, light traveling speed, and then from there I'll get an interference. So I can calculate any speedy event which is occurring, but can be converted into a retardation event. This is how it is being explained. And normally I also don't want to get into those details, because we are almost closing. Maybe tomorrow I can quickly touch upon this if you wish. That what happens is here that I will have straight away in an FTIR spectrometer. What happens is that your frequency, what we'll do is that, so I'm not writing the expression, so I request you, it's normally a numerical solution, so I will skip it because it may not be that suitable for you to discuss now here, which is again require a long time for me. I will put a retardation. So this is easier for me to put up. So this is how it comes out, and this is your delta V bar of an FTIR machine. So if I have a mirror which is moving with the speed of delta, I can able to have, suppose I define the frequency in which the mirror is moving, which can be connected to delta V straight away as inverse of the distance traveled by the mirror in the given cycle. Okay, so for example, if I want a resolution of 0.1 centimeter inverse, I will be able to apply the same resolution. So 0.1 is equal to 0.1 centimeter inverse is equal to 1 by 2. So tau will be roughly around how much? 10 centimeter inverse. So taking one round, it will take 5 centimeter. The mirror will travel in a Michaelson interferometer. Okay, and then comes back. So I get 0.1 resolution. So this occur in time domain and converting into frequency domain. So there are plenty of equations available for converting this. I'm saying the basic use of it. I don't have much time to explain that. Of course, we can start from the basic expression y is equal to sine a sine 2 pi v1t plus 2 a1. So I can start this expression so that you can convert the frequency into time domain and then put it back. So we normally take an integral of all of them. So we take integral of minus infinity to plus infinity and calculate it. Okay, instrument will do it and give you the time domain converted into frequency domain, and a spectrum can be occurred in seconds literally by doing this Fourier transformation. This is called Fourier transform spectroscopy. So FTIR is called a Fourier transform spectroscopy, which is basically advantage of using an interference filter, interference device. Okay, fine. So if you are more interested into it, I encourage you to check. There are some very good YouTube videos available about it. Okay, I mean, so even if I touch, I will only show you the real part of it. Imaginary part is even more complicated. I was telling you that the theta is calculated on the complex circle, then it have imaginary part also coming into. Then you can see this YouTube channel, some M Brown or something, I forget, the M4B or something. You can see that. Maybe I can share with you some of your interested. It's a beautiful animation, shows, will give you a visual introduction to how the Fourier transform is done. Okay, so maybe useful for the students to understand the basics of how the FTIR is being done or if Fourier transform is done, then going into its detail. Then, when we are, so okay, I just want to also tell you this, like, when we are asking a student a lot of questions in an interview, so all on a sudden, say a professor is asking, why sky is blue? So in spectroscopy, you can expect such a question, very, you can expect a very cute question from a teacher, and you may need to explain it why. You can think about the possibilities why. And another question that people normally ask is that why sunset is orange tint in color, orange, what is it, pale tint orange color. Why sunset shows it? Why sun is yellow? Okay, these are the questions you normally expect and immediate. I mean, that has a definite answer, right? So you may need to get prepared when you try to go for interviews or writing exams. So I mean, I don't know like which way I can able to give you more information. So we will see that. So these are the questions you can just search it in the internet. You will get immediately the answer why it is happening. I'm not going to give an answer to that. Okay, so I think that's enough. I think we are almost done. Tomorrow I will quickly introduce rotation and vibration and see how that will be beneficial to you. I mean, I'm not getting the satisfaction I'm touching. I just thought of I have to give you something like in a capsule, but I don't know how does it useful for you guys. But if you have any specific doubt, I'll be happy to answer. Yes, please. I think I'm done. Shall I?
Yeah.
Okay.
Students, do you have any questions in your mind? I think there will be a lot of questions, I'm sure, but students usually will be hesitant to ask because most of the students, I mean, at least at the degree level, they are getting introduced to the spectroscopy. So I think they have to reflect on these topics, especially these things which were talked about. The fundamental, of course, the refraction and how these fundamental equations are related to these instrumentation part was interesting. So maybe students are not exposed to those kinds of textbooks, or they're not exposed at this stage. So I don't know whether they have any very specific questions. Please, students, use this opportunity to take up some questions.
I can stop presenting. Shall I stop presenting, or then I can answer? Right? Maybe that may be easier. Otherwise, you see mirror screen. Yeah.
the interaction part is the weakest part here, what we think, especially as you
Right.
explained.
So I mean, the whole point is that when you deal with spectroscopy, it is not easy to even discuss. Actually, that's I was also trying to skip many things. I mean,
Yes.
I feel it's not good actually. Like if like a normal classroom that you introduce basic spectroscopy is quite hard. Anyway, so but I mean, at least I hope that I have given something that students can later look into seriously, like some of these aspects in detail. But what we normally see here, that spectroscopy is directly connected to research. So if they use it, I mean, learn it from the basics. I mean, that basically good for them. That that can be translated into good knowledge. That start from. That's why we are also introducing a part of instrumentation itself. So we took some of our curriculum has been recently revised to content, to make the content which is meaningful for the students. We are following some MIT open course manual so that the spectroscopy we have a course which is happening on spectroscopy and other physical methods. Along with it, we teach them how to do spectral measurements or our system. So that basically make them, like suppose I measure a spectrum like Kamina 4, you may have used spectrometer there, right? So the student will get it and then they measure it and then open the spectrometer and see what are the components. So that basically help them to learn about it much better, and then even they understand the spectrum from the basics, and then and how the machine is measuring it, so forth. Will give them a lot of information so that they can even improvise it later. So that was the idea, but that's why I went off road a little bit and then coming back to that part, because maybe at some point of time they need to have this.
But the basics were all there, sir. The interaction with matter and how the instrumentation comes about, the Beer-Lambert's law. All these are part of the BSc syllabus.
Okay, yeah.
So they have gone through all this. Only thing is to correlate it with what they're studying. So
Yeah, even
it
the
is a
instrument.
good way of bringing about the introductory parts, I would say. Yeah.
Okay. I'll be happy to take, yeah, that's what I also want some feedback, so that maybe tomorrow, my idea was to start with rotational states. I mean, that's rotation.
Yes, that's how it goes for us too. Rotation,
Right.
vibration, and then
Right.
electronics.
So, but there is also one problem, the rotation, they never do it in lab. We we have only few places rotation spectroscopy is being used. But it's actually one of the beautiful fundamental tools.
Microwave.
Yeah, that you can pinpoint, exactly calculate the bond length of a bond and so forth. So it is actually very good, useful tool. I will see. I will try to cover rotation and vibration like in 1 hour, 1.5 hours. Maybe challenging, but I will try. Maybe. So, pardon. I mean, I don't know also how to make it in actually a capsule, because I am giving such kind of a capsule talk first time. Okay, so be happy that if you can give me some good feedback. So
Yes, today's was good. Only thing is, for them, they have to get that. Actually, the 5th semester students have actually studied all these spectroscopic techniques.
Okay.
And consolidating it with the instrumentation part, with the monochromator and the gratings, that should do it actually.
Okay, so that's great. So I know maybe online it will be very difficult even to interact with students. So
getting them to interact, you can interact, but getting them to interact is a difficult part. But they put questions in the feedback form, which we share after this talk.
Great, yeah. Thank
Probably
you.
you will get the questions tomorrow.
Yeah. Thank you very much. Yeah, we will see you tomorrow then.
Yeah, sure.
Yes. Yeah.
Okay, Jino sir.
All right. Thank you so much, and see you around tomorrow at the same time.